Hello everyone, myself Niyar. So today I will be presenting you the topic static load carrying capacity of a rolling element of bearing. So as we know, some bearings have less amount of load carrying capacity. So basically here is what a bearing looks like. So as we know, this is a bearing, but the most important thing for it is its load carrying capacity. So we don't know that how much amount of load this can it resist. So let me tell you some basic introduction about our topic. So understand the static load carrying capacity is fundamental to proper bearing selection and mechanical system design. This presentation explores the mathematical expressions, factors, and engineering principles that governs how bearing withstands and how without rotation, without loads and rotation, means how it resists the load and how it withstands our applied load. So static load carrying capacity. So what is static load carrying capacity? So it is basically that it represents the maximum load of bearing can support while stationary or oscillating at very low speeds without permanent deformation. So we know that the bearing should not get any deformation. So it's the most basic property of the bearing that it should not get deformed due to existing load. Otherwise, it will be impacted to the machine. So it is very critical concept because excessive static loads cause permanent indentions at the concept points between rolling elements and races. So it will be hazardous to our element or our machine. Key definitions and parameters. Basic static load rating. So that is called defined, that is denoted as C naught. The static load that produces a total permanent deformation of 0.001 times the rolling element diameter at the most heavily loaded contact point. Equivalent static load that is denoted as P naught. A calculated load that produces the same contact stress as the actual combined radial and axial loads acting on the bearing. And lastly, static safety factor, that is. So let me derive the mathematical expression for the static capacity. The basic static load rating depends on bearing geometry. So ball bearing has this law or these fundamentals that C naught is equal to F naught Iz dw square cos alpha, where F naught is a factor based on geometry, I is the number of rows, and here Z is the number of balls per rows. Here dw is the diameter and constant angle, and for the rolling wheel the derivation is C naught is equal to F naught Iz LWE and dw cos alpha. For here the roller LWE is effective roller's length. So these are the expressions for bearings. Factors influencing the static capacity. So let me tell you how it affects the bearing for deformation. So rolling element size affects the deformation. Contact angle affects the bearing. Also number of elements, mathematical properties affect the bearing. So these are some factors that affect bearing size or any deformation that takes place. Static factor capacity of requirements. This is the graph in point that some are highlighted as smooth operations, normal conditions, high reliability, shock loads, and critical systems. So this is the graph evaluated for more importance, according to more importance of the bearing deformation. Coming to next, here as I have shown before the bearings. Practical design examples from problems meaning like some examples have been here included. Practical design example. So what are the key takeaways? Capacity expressions, load calculation, and safety margins. These are some key takeaways. So that's for today's presentation. Thank you.